In this video, we're going to talk about random functions associated with normal distributions. So in particular, we're going to talk about things like the mean, the sample mean, and the sample variance. These are kind of the two biggest sample statistics that you're interested in when you start doing statistics on data sets. So a lot of times these distributions that the statistics are drawn from are coming from a normal distribution. So let's analyze the normal distribution a little bit when you start doing things like adding things up or taking the means or looking at the variances and so on. So let's look at this theorem that says that we start with x1 out to xn being mutually independent normal random variables and giving the various means and variances. Then the important part of this is that the y is a normal distribution. So the sum of normals is normal. We add the means and then we also add the variances, but we have to square any constants that come in front. So like we had before. So the way we see this is that if you look at the moment generating functions like we did in the previous section, we know that the moment generating of a sum is the product of the moment generating functions. This is your moment generating function for a normal distribution, right? It's the mean times t plus the variance times t squared over 2. We're putting in c sub I t for t, so that's where that's coming from. And now here we're just rearranging things and putting the c sub I and the mu sub I together, and the c sub I squared and the sigma sub I squared together. And then we recognize this now first as a sum of these, right? When we multiply, we add exponents. And then we can break this up now, and now I've got an exponential to a sum of the means here, a sum of the constant multiples of the means, sums of the constant squared multiples of the means, or the variances I mean. And we recognize this is a moment generating function of a normal random variable. This is the mean, this is the variance. So again, this is where your moment generating function technique is coming in handy to be able to identify distributions. So a very special one of these would be the mean of a random sample. So if we start with a random sample, all the variables coming from a normal distribution, the same normal distribution, and then calculating the sample mean where your constant's always 1 over n, then we get our mean is mu and our variance is sigma squared over n. Let's see how this works. So we're going to let our c sub I equal 1 over n. So then the mean is going to be 1 over n times mu. Sum them up. Pull the 1 over n out. Here we're adding mu to itself n times, and then your n's cancel. So you really do get that the mean stays the same. How about the variance? Well, remember this time we square the constants. I can move that out in front. Sum of all of these variances is n times sigma squared, and then you'll get an n that cancels, and that should be, over n. This should be a fraction. This should be sigma squared over n here. So make sure if you put that in your notes, you have it over n, not just a sigma squared. Okay. This should be this value up here. All right, so this kind of makes sense, right? If you think about doing the mean, well, if you think about the mean of all the means, it should have the same expected value as the individual random variable. However, if you think about taking a random sample and then adding it up and getting the mean, take another random sample, get the mean, take another random sample and get the mean, you would think that the variance would go down. You think you wouldn't get as much spread in the means, because even if you have a wider spread for a random variable, if you take a mean of things, some of them will be above, some will be below. You should be averaging things out if you have a sample, if you're going to take the mean. So you would expect that the variance would go down, and that's exactly what's happening here with the n in the denominator. All right, let's look at this now and analyze the sample variance. So the sample variance looks a lot like our definition for variance when we did an expected value, except that we subtract off the sample mean rather than the population mean, because usually we don't know what it is. And instead of dividing by n, we divide by n minus 1. The reason why we divide by one fewer than the number of elements in your sample, it will become apparent here. When we take n minus 1, so clear your denominator, and divide both sides by the population variance, you get a chi-squared random variable with n minus 1 degrees of freedom. What happens here a little bit, if you think about it, is that we're estimating, and this is something we'll talk about next semester in statistics, you're estimating a population mean, a population parameter with a sample. Anytime you lose that, you end up losing a degree of freedom. So notice we have degrees of freedom here in randomness for being a random sample, but we're going to lose one of those degrees because we approximated a population random variable, or a population parameter with a sample statistic. All right, we're not going to prove that these two random variables are independent. That's something you'll prove next semester. So we'll focus on the second statement. All right, so this random variable starts out as being chi-squared of n. The reason for that is we have a standard normal distribution here because we subtracted the mean divided by the standard deviation. When we square a standard normal, we get a chi-squared on 1 degree of freedom. When you add independent chi-squareds, it stays chi-squared. You just increase the degree of freedom by 1 for each summand. So that's why we've got chi-squared of n. So now let's do some rewriting. Let's add and subtract x bar in the numerator. We expand. We distribute our sum over the sums and pull out things that are constant with respect to the sum. In particular, this piece right here is constant. It doesn't have, I'm sorry, not that piece. This piece right here is constant. Doesn't have any i's in it. This, when you add those all up, you get 0. So this term goes away. This is a bunch of constants that we added to itself n times, so you just get n times that constant. Okay, so now look at this piece here. We've got something that looks like a bunch of chi-squared random variables, but not quite, because we don't have the mu here. However, it does look like what we're trying to deal with, right? If I think about taking the sigma squared out here, this is exactly the n minus 1 s squared over sigma squared. Okay, this piece here is chi-squared of n. We just said that a little bit ago. This piece here is chi-squared of 1. This piece here is filling in the blank. So it makes sense that it's going to be chi-squared of n minus 1. So let's see why that's true. Looking at this piece here, we divide, if we divide into the parentheses here with the square root of n and move it to the bottom, we've standardized this random variable, made it normal 0, 1, so it's chi-squared of 1. We just mentioned that on the last slide. So now we rewrite w in this form. Certainly if s and x bar are independent, s squared and x bar are independent, so are this s squared and z, because z is the only thing it depends on is the x bar. Now let's use some moment generating functions. This is chi-squared of n. Here's its moment generating function. Here's how we calculate moment generating functions. Here's what w is defined as. Break up the product with the sum, and then break up the expected value over the product. This is chi-squared of 1, so its moment generating function is just 1 over 1 minus 2t to the 1/2. Now clear your fractions, and you get the moment generating function for n minus 1 s squared over sigma squared. And we see that it must be chi-squared of n minus 1, because that's the way the moment generating function looks. So in this case, we get that this particular random variable is chi-squared of n minus 1. All right, one definition here that you'll pop up with next semester, but we're not going to do much this semester, is what's referred to as the student t distribution with r degrees of freedom. So it looks like a normal random variable, or a standard normal random variable on top, and a chi-squared of r degrees of freedom on bottom, divided out by its degrees of freedom. When you see this, you get a t distribution, and it's going to pop up next semester in certain statistical analyses you do in the future.